Is silicon-based life possible? Is there evidence of silicon-based life on Earth or any place else? Maybe it should be called the life paradox. It seems that for all its complexity and diversity, and in modern times its science and literature, life on Earth has its foundation in only four simple elements: hydrogen, carbon, nitrogen, and oxygen. Evolution and complexity accrued additional elements to species designs, such as phosphorus and sulfur, but to this very day, all proteins, carbohydrates, and fats are merely combinations and varying amounts of the original four elements. Based on the periodic table of elements, granite appears to be just as complex as living organisms. The element that makes all the difference and deserves our special thanks is carbon, the key ingredient on which all life on Earth is based. Carbon takes the central position in organic molecules because it is the atom best suited to bond with other atoms to create long, life-giving chains. There's no magic or miracle to it, just a natural consequence of the configuration of electrons that chemists aptly call electron configuration. Electrons speed around atomic nuclei in tight orbits called shells. Every atomic nucleus is surrounded by concentric layers of shells, and each shell can only contain a certain maximum number of electrons. A shell is subdivided into orbitals, each of which carries its own prescribed number of electrons. Electron configuration can be looked at this way. K, or 1, is the first shell, which has one s orbital that may contain 1 or 2 electrons. L, or 2, is the second shell, which has an s orbital and a p orbital. The p orbital can have between 1 and 6 electrons, after 2ks is full. The same is true for M, the third shell, which consists of s and p orbitals. In addition, there exists a d orbital that can accommodate from 1 to 10 electrons, after 3p is full. The elements of the periodic chart are configured up to Q, or the seventh shell, but it won't be necessary to explain that far because the elements of life that we are concerned with only involve the first 3 shells. Let's take hydrogen for example. Hydrogen has only 1 electron in its one shell, so in electron configuration it would be written 1s1. The s orbital still has room for another electron, and that's the essence of elemental and molecular bonding. Another element missing an electron could easily join with a hydrogen atom to fill the orbital. The case of helium, however, is vastly different because helium is configured 1s2. As you can see, its orbital and thus its shell are full. It cannot bond with anything, so it cannot form molecules. Now it's time to talk about carbon. Carbon has an electron configuration that suits intelligent life best, not only here on Earth, but probably everywhere else in the universe. It is possible that life on other planets is based on another atom, such as silicon, but only carbon can form the long, intricate molecules needed to produce complex life. This is how a carbon atom is configured. The 2 electrons in the p orbital mean that there's still room for 4 more electrons that would provide a firm, stable bond. Electrons from perhaps 4 hydrogen atoms would bond nicely. Nitrogen with a half-filled p orbital also bonds well. An oxygen that is in search of 2 electrons would make a great bond with 2 hydrogen atoms. This is why water is so abundant in the galaxy. Furthermore, 1 carbon atom can bond with 4 oxygen atoms, and those oxygen atoms can bond with other elements to fill the p orbitals. This could go on until the molecules formed are of great lengths and complexities. The 4 elements, hydrogen, carbon, oxygen, and nitrogen, were attracted to each other as soon as the waters of Earth cooled just below the boiling point of water. This probably occurred about 4.4 billion years ago. It seems that nitrogen and hydrogen bonded together to form an ammonia molecule we now call the amine group. Another molecule made of carbon, hydrogen, and oxygen formed the carboxyl group. A third molecule, carbon, hydrogen, plus other elements like phosphorus and sulfur formed the varied group. When the three groups bonded, they created the first amino acids. Amino acids are what proteins are made of. The varied group gives us more than 500 amino acids found on Earth. Humans need only 20 different types. Carbon, oxygen, hydrogen molecules also form fats and carbohydrates, all the components of life. What we really want to know is, where is the silicon-based life, and is there any on Earth? And the answer is that, as yet, no one has found any, and there are no traces of silicon-based fossils. But why? When we look at the electron configuration of silicon, we see that it indeed has 2 electrons in its p orbital, and that gives it room for 4 bonds. However, that particular p orbital is in the 3 shell, the 3rd energy level, a farther distance away from the nucleus than carbon's partially filled p orbital. The extra distance where the silicon bond takes place means that there's less positive energy from the nucleus anchoring and supporting the negative electron bonds. The force of attraction from the nucleus makes a significant contribution. Thus, carbon can form longer, more stable organic molecules. In addition, the closer proximity to its nucleus allows carbon to build better multiple bonds. There is some talk that silicon is a metal, and as such forms metallic bonds. This is not true. A metallic bond is a heavy, overlapping electrostatic bond. Silicon is not a metal, or even a semi-metal. It has some metalloid properties, but it forms covalent bonds, just like carbon. This means that the outermost electrons of the atoms making up the molecules are holding hands. They're sharing orbitals. Being metalloid does not prevent it from developing life. Silanes, silicon-silicon bonds, and silicon-hydrogen bonds can be long enough to support life, but these bonds are so reactive that they would destabilize and break down before complex life could evolve from them. This doesn't mean that simple silicon-based life is impossible, but it is doubtful that it would get much further. Silicon oxide bonds would present another problem. The electron attraction between silicon and oxygen takes precedence over all other enticements, and the silicon-oxygen bond is too strong for organic life. In other words, once silicon and oxygen bond, it would take a crowbar to pry them apart. The oxygen would essentially close off the silicon to other atoms and molecules. The vast majority of silicon-based molecules would be crystalline silicon dioxides, which to the geologists are commonly known as quartz and opal. For any hope of complex silicon-based life, oxygen would have to be virtually absent from the environment. But since oxygen is the 3rd most abundant element in the universe, it seems that no intelligent silicon-based life is a foregone conclusion. And so on Earth and throughout the universe, the instability of the silicon-based amino acids and the presence of oxygen makes silicon-based life next to impossible. Thanks for watching. Talk to you soon.